Hello everyone, welcome back to the channel. So today we are doing Leetcode 342 power of 4, and it's a very simple question. You don't actually even have to read what the problem statement is. It says given an integer n, return true if it is a power of 4, otherwise return false, right? So the only input that we have is a number, and what we have to do is we have to check whether it's a power of 4 or not, right? So what I've done over here is, what I'm saying is we'll start from the brute force approach. And the brute force approach obviously is that we list all the power of fours and we see if our number matches any one of them, right? So what we are going to do is, whatever our number is, we are going to start from 1. I'm going to see if 1 is equals to 16 or not. No? Okay. Then I will check if this is equals to my number. Still no? No problem. If this is equals to my number, if it is, I'll just return true, and I will continue this for a certain number x, which will be determined by the constraint that we have, right? So if I look at the constraint, I will know at what limit I need to stop looking, right? So I will check that through the constraint, and then through simple comparison we can very easily establish the answer of this question, right? So how we are going to do that is, as you can see over here, the constraint at maximum can be 2 to the power 31, right? Now what does 2 to the power 31 actually mean? Let's see. So I have 2 to the power 1, then 2 to the power 2, then 2 to the power 3, 2 to the power 4, so on and so forth. 2 to the power 2 is actually 4 to the power 1. Similarly, 2 to the power 4 is 16, which is 4 to the power 2. And why that's happening is because 4 in itself is 2 to the power 2, right? So this is equivalent to this, and this is actually equivalent to this. If I multiply the powers, it becomes 2 to the power 4. So that way, if I'm talking about 2 to the power 30, 2 to the power 30 is nothing but 4 to the power 15. And since we are talking about 2 to the power 31 minus 1, you would notice we don't actually, we never reach 2 to the power 31, right? We never reach that exact number. So the largest power that I have to worry about is 4 to the power 15, right? Having established that, let's now see how we can do that very simply inside our coding environment. So what I'm going to do is have a loop for int I equals 0, I is less than what? 15, I is less than 15, or less than equals, or let's say let's less than 16, I plus plus. All right. And what I'm going to do is I'm going to left shift 1. So left shifting 1, what does that mean? Left shift 1, what does that mean? So you know for a fact you have 1, 2, 4, and 8 in binary, right? And if I have a decimal 1, it's just 1, 0, 0, 0. If I left shift it one time, it becomes 2. If I again left shift it, it becomes 4, right? So left shifting basically means you increase the power by 1. So if you have 2x plus 1 and you apply the left shift operator, you're basically doing this, right? So what I'm going to do is I'm going to say, okay, if 1 left shift I times, if I left shift 1 I times, I hope it's the correct syntax, probably. If this thing, if this thing, it, if I do that and it becomes equals to, but no, there is one thing which is I think wrong with this approach, and that thing is that I'm not looking for powers of 2, I'm actually looking for powers of 4. So this approach won't actually work. So what I'll just simply do is I will take an int num as 1, int num equals 1, and I will have a loop, something like for int I equals 0, I is less than uh, 16, I plus plus. I'm going to see if num um, if num equals the input that I'm given. If this is true, return true. Otherwise, what I'm going to do is I'm going to multiply the num by 4. Right, perfect. And over here, I'm going to return false. Let's see if it passes the example test cases. it does not, because I will have to take this probably as long. Let's see. It does. If I submit it overall, let's see if it passes all of the test cases that we have, and it does. But what you will observe in the follow-up question is that they're saying, could you solve it without loops or recursion? And what we are doing is we are using a loop, right? Even though it is a constant time loop, but is there any other way that we can solve this question? What do you think? So let's see. Let's actually think about that. I accidentally opened my VS Code. Let me close that. Okay. Now, if I think about all the powers of 4 that I have, 1, 4, 16, 64. Let's see if I can derive any sort of um, you know any sort of relation between what all of these numbers are. Right, 1, 4, 16, 64, and what is 64 multiplied by 4? It is 256, I think. Yeah, 256, right? So what I'm thinking is, if uh, first of all the number should be greater than 0, where if it's a negative number we just directly return false. We'll just directly return false, right? And apart from that, what I'm seeing is 4 minus 1 is 3, 16 minus 1 is 15, 64 minus 1 is 63, and all of these numbers, what I'm observing is all of these numbers are divisible by 3. So if I divide them by 3, I get a 0, right? And so this is one property that I have found through observation, subtracting minus 1, right? And the other property is that since I'm talking about powers of 4, so 1, 2, 4, 8, 16, 32, 64. Since we are talking about powers of 4, so it could either be this, it could either be this, or it could either be this, so on and so forth. What you'll observe is that if you want to know how many bits are on in any power of 4, or even if we are talking about any power of 2, then it's just a single bit which is on, right? So if I take these two properties, number one property mod 3 equals 0, number n minus 1 mod 3 should be equals to 0, and if I take this property as well, which I will be able to find out using the pop count function, the built-in pop count function in CPP STL. If I combine both of these conditions along with this particular rule, let's see if I am able to pass all the test cases that I have. So what I'll just say is, if n is greater than 0, and n minus 1 mod 3 equal 0, and what else do I have? What else do I have? One bit is on, so you have the built-in pop count, right? And it's written something like, I think, built-in pop count of n should be equals to 1, which tells me that there's just a single bit which is on, and which is 1, and the rest of them are 0. So if this is the case, you return true, otherwise you return false, right? So if I submit this code, let's see if it passes. It does, right? So you are successfully, just by a little observation, you are very successfully able to solve this question without loops or recursion. And there is this one more approach which I would like to share over here, just for the sake of your learning. You could do the same implementation of this particular question using a bit set as well. So if you don't know what a bit set is, let me show you. Bit set CPP-STL and C++ bit set and its application. You could have implemented this very same thing that I have done, this very same thing, by using a bit set as well. So this is how you initialize a bit set n name. So it's not actually an integer. I wrote an integer over there, but it means how many bits do you want to take. So for example, since it's 2 to the power 31, what 2 to the power 31 minus 1, so what I will do is I'll take 30 bits, or let's, whatever, let's just take 31 bits, why not. And I'll just get give it a name, let's say bits. What I will do is, since you already know this, that what I actually want to do is, by the way, I missed one of the test cases over here, 64, and there could also be just this single one, right? So what I will do is I will check this particular index plus 2 this particular index plus 2 this particular index. So I want to know the powers of 4, right? This is 4 to the power 0, this is 4 to the power 1, this is 4 to the power 2, so on and so forth. So what I can very simply do is have a for loop over here. So can we have a for loop? Let's see how do we actually iterate over a certain bit set. Can I do that? Can I iterate over a bit set somehow? Let's see. So if I have for int I equals 0, I is less than 32, and I plus equals 2, what I will do is this. So bits of I if bits of I fits equals to 1, so um if for example this is equals to 1, if this is equals to 1, or plus 2 this is equals to 1, or plus 2 this equals to 1, then in that case I will return true, and otherwise what I'll do is I'll return false. All right, so if I submit this, I think if it passes the example test cases, it's probably going to pass all the other ones as well. But why is it not passing? False, output false, expect true. Why? Bitset 31, am I missing anything? um what am I? Oh, I actually have to initialize it as well. So yeah, obviously I have to initialize it as well. So what I'm saying is, whatever the input number is, that is what I want the binary representation of. So this is nothing but binary representation, right? But what whose binary representation do you want? Of n, right? So you'd have to initialize it as well. So yeah, it does not pass all the test cases. Why? It says output as true. Why does it say so? It shouldn't at all say something like that. So if I think about it, 5 is 5 is actually what? Uh, so you have 8, 4, 2, 1, and 5 is 1, 0, 1. And this bit is on, but what I'm doing, this bit is also on, and I don't want this bit to be on. Yes, that makes sense. So what I will have to check is also this. So dot count if bits dot count is not equals to 1, you just return false, right? And also if n is less than 0, sure, why not? If n is less than 0 or this, return false in that scenario, right? So let's see if it now passes all the example test cases. It does, right? So I just wanted to share this thing because I even this is the first time that I have learned the bit set, so I thought why not share it with you guys, right? I hope you found the video helpful, and I will see you in the next one.